Right now we're going to continue with a lesson on complex numbers, and in particular something very neat that we learned from polar form. From polar form we learned last time that if z were to be raised to the n, and if z originally was just r, in cis notation, of course, right now, we would write that as cosine of theta plus I sine of theta. If we were to raise z to the nth power, we saw from our last lesson that we had a wonderful shortcut. It would allow us to not have to algebraically multiply a plus bi to itself so many times, n times in fact, and a wonderful shortcut. Well, z raised to this integer power, like z raised to the second and fourth and so forth, is wonderful. But today we're going to investigate how to find roots of complex numbers. And we're going to use this idea that I just wrote up. And officially this is known as de Moivre's theorem. But let's just say that for an example, I'd like for us to find the 3 cube roots of I. And for that matter, we could find roots of all different types of complex numbers. But let's begin by making an Argand diagram of I, which, by the way, I is really 0 plus I if we write it in a complex number form. Now, if we were to graph this out, we'd have our reals, we'd have our imaginaries. I hope you'd see very, very quickly that, of course, we have 1 out in front of I, so we would go up 1 unit on this imaginary axis. That's what this angle would also pertain to, an angle of pi over 2 radians. So I, if we were to write that in polar form, it would be a radius of 1 times the cosine of pi over 2 plus I sine of pi over 2. Now you might have noticed I also have put quite a bit of extra space there. Hopefully you know as well that pi over 2 is just one angle that would be terminating at the point that we'd like to. We could just as well have written plus 2 pi k. Now that might seem a little odd at first. You might wonder, well, my goodness, shouldn't we just choose one simple angle? And of course the simplest angle would be best. Normally that would be the case. However, we're going to say, my goodness, what if we wanted to take the third root of I? Well, when you take a third root, there will be 3 answers in this complex plane. If we took a fourth root, the fourth roots, there'd be 4 of them. So what we're going to see is if we have n roots, we're going to have n solutions. So a third root, a cube root, is going to have 3 solutions. Let's see how that would be the case. If I gave you I to the 1/3 power, that's how we'd write the cube root. Using this idea that we just had up on top, essentially we'd say, why not take this as 1, the radius out there, to the 1/3 power, and that's actually really nice. That's going to work out quite well. But you'll notice that then we're going to take 1/3 times theta. Now 1/3 times pi over 2, of course, is pi over 6, isn't it? But don't forget, we're also going to take 1/3 of 2 pi k. And what would that become? 2 pi over 3k. My goodness, look at that. Similarly, we'd have pi over 6 plus 2 pi over 3k. What I want you to notice is that this new angle that we now have inside our cis notation, if we were to let k equal 1, our angle that we get by adding that to pi over 6 would no longer be coterminal with pi over 6. It wouldn't necessarily stop at the same location, and it definitely won't. So very quickly, I'd like for us to just investigate what's happening here. If k is equal to 0, well, that's maybe one of the easiest things. And by the way, 1 to the 1/3 is just a 1. We'd be at cosine of pi over 6 plus I sine of pi over 6. It's wonderful when our radius out in front happens to be a 1. If it would have been something different, like if 1 to the whatever radius to that fractional power is, whatever you'd get, you might even get a radical out in front. We'd have to just distribute that to the cosine and the sine. By the way, we know that the cosine of pi over 6, by the way, is going to be radical 3 over 2, and the sine of pi over 6 is 1/2. So we could even say I times 1/2, or I over 2 more simply. Now if k is equal to 1, I want you to notice that we'd have pi over 6 plus 2 pi over 3. Getting a common denominator, we'd have 4 pi over 6 plus 1 pi over 6. So you could see very quickly we'd actually wind up with the cosine of 5 pi over 6 and the sine of 5 pi over 6. Of course, we have our I out in front. Now, of course, this is the same reference angle, but a different quadrant. 5 pi over 6 is in the second quadrant. We know that cosine will be negative there. So we'd actually get negative radical 3 over 2. Sine, however, will be positive, and we will be left with this, negative radical 3 over 2 plus I times 1/2. And by the way, I think I'll just write I over 2. Maybe that would be written perhaps a little bit easier. And then finally, if we were to take k is equal to 2, well, k is equal to 2, you can see very quickly you'd have pi over 6 plus 4 pi over 3. Now 4 pi over 3 would be 8 pi over 6. And if you add 1 pi over 6 to 8 pi over 6, you'll have 9 pi over 6. But what is 9 pi over 6? Reduce out a 3 from the top and the bottom. You will have just 3 pi over 2. Wow, would you look at that? This is actually maybe one of the easiest things to work out. Cosine of 3 pi over 2 is just 0. Sine of 3 pi over 2 is negative 1, so we'd have a negative I. So very plain and simply a negative I. There you have it, your 3 cube roots of I. Now, we could definitely check this with a calculator. Of course, our upcoming contest will not have a calculator allowed. But I do want to point something out. There's a wonderful fact that if you were to look at the first angle being pi over 6, and if you want to think about that as 30 degrees, you certainly could. It would be equivalent to that. Think about it this way. 360 divided by 3 would be 120. If we've got 3 cube roots, 3 solutions, we'd have an answer every 120 degrees. Or an answer every 2 pi over 3 degrees. You can think of it that way. Well, if you add 2 pi over 3 to pi over 6, you'd be at 5 pi over 6. Think of it this way, 120 plus 30 is 150. Another way to look at it. Similarly, when you add 2 pi over 3 to 5 pi over 6, you'd be down here at 3 pi over 2. What are we seeing? It's as if we are on a circle. In this case, the radius would be 1. You could say it's a unit circle. And our solutions are equally spaced at 2 pi over 3 radians apart, or 360 divided by 3 degrees apart. That can be very helpful. We'll see why in just a moment. But let's take out a calculator for a minute, and we'll just see if the answers we came up with are in fact going to make sense. Hopefully they will. Let's get the calculator out, and we'll type in the square root of 3. We can say divide by 2. Now I'll say plus. Now I is right above the decimal. Second decimal is I. We'll say I all over 2. You see, if I found a cube root, that means when I raise that up to the third power, I should go back to our original value of I. Now, of course, I could very quickly confirm this. I could bring this back and just get a negative in there. Let's see, insert a negative. Oops, got that out in front. Meant to put that over here. Sorry about that. It would only take a moment to confirm that. You could just hit enter. Look at that. You could say, well, wow, I've got negative I as well. If I took negative I and raised that to the third power, well, we could even do that on our own without the calculator, but you'd see, hey, all of those complex numbers, you raise them to the third power, you're back to I. This would be confirmation that these are, in fact, the correct answers. Now, mind you, we're not going to have a calculator when we take our contest, but just wanted to help you out with another question. What if we wanted to find the 3 complex roots of 8? Now, usually you say the 3 complex cube roots of 8, I should say. Meant to say that. Find the 3 complex cube roots of 8. Usually kids will say, well, hey, the cube root of 8 is 2. Yeah. But look, even if you know for a fact that one of your answers is a 2, well, let's think about this. We're going to go 2 pi over 3 over, and I'm going to have a radius of 2, so this is going to be at an angle of 2 pi over 3. Wow, reference angle of pi over 3. I'm going to find another solution right over there. Where would my other solution be? Well, 2 pi over 3 after that. Remember, with cube roots, it's 2 pi divided by 3 for each time when we add. So we'd have another answer over here at an angle of 4 pi over 3. Of course, we'd still have a radius of 2 out in front. Why am I showing this to you? Well, you don't always have to use that theorem that we just made reference to. You can use this as a shortcut. Now, of course, you know that this is 60 degrees, pi over 3, and hopefully you know in a 30, 60, 90 right triangle, even making this a lot quicker for you. Opposite of 30 is A, opposite of 90 is 2A, this is A root 3. So very fast we could say this is 1 and this would be a radical 3. Likewise, this would have to be a 1 also. So what are my cube roots? 2. Now look, I'm going to go root 3 to the left, but then I'm going to move up 1 unit in the imaginary sense. I'm going to go root 3 to the left, but then I'm going to go down 1 unit in the imaginary sense. Look at that. We certainly could have done this problem the same way that we did the first. When I say that, I mean we could have said here's 8. You know, I've got a radius of 8. I've got a cosine of 0. Here's 8. Cosine of 0 plus 2 pi k, and then we'd say plus I sine of 0 plus 2 pi k. And then we could say, well, hey, let's take a cube root of that, and all of a sudden you'd say cosine of, well, you can see more or less it's going to be 0 plus 0 divided by 3, of course, is just going to be what we had before. You'll see you wind up with exactly the same thing. It's just that this is a lot more work. So knowing that shortcut on the unit circle or on an equivalent circle with that given radius will allow you to get some answers more quickly. Okay, well, we're going to have another video coming up on how we can solve equations involving complex numbers.